Now that we've spent quite a bit of time exploring the polynomial and rational functions and their graphs, we're going to start looking at inequalities that involve those two types of functions. We'll start off with polynomials. Now, some underlying ideas that are going to help us out with this are going to be just the graph, the general graph of these two types of functions. So consider polynomials for a moment. We know that polynomials are smooth and continuous. We've talked about these two ideas, but it means there's no holes, there's no gaps, there's no asymptotes. The domain for a polynomial is all real numbers. Right, so these are just some things that are going to help us out. So you can draw the graph without lifting your marker or your pencil off the paper. All these things are true about polynomials. And so those things all come together to show us that when you draw the graph, that gives you an idea of what the function looks like. The only times that a graph of a polynomial can move from positive to negative or from negative to positive is by crossing the x-axis, okay, at an x-intercept. Now, this is just one example. It would be potentially a cubic function with a negative leading coefficient, graphs like this. But you could have anything. You could do like a quartic, maybe with a positive leading coefficient. But again, the only times where your graph can go from positive to negative or negative to positive or any of these sign changes in the output is by going through the x-axis. Has to go through the x-axis in order to go from one side to the other. It can't jump magically from one side to the other without going through that boundary, okay? Now there are times where it may hit the x-axis but not go through, right? If we had an even multiplicity on a zero, we've seen this before, where the graph can touch the x-axis but not go through. So there are many things that could happen at an x-intercept, but the main thing is the only places where a graph can switch sign, the outputs can switch sign from positive to negative or from negative to positive, can be at x-intercepts. Of course, not every x-intercept will make that occur. You could have a positive to a positive or a negative to a negative, but either way, the only places where it can switch sign is on the x-axis at an intercept, okay? Okay, so that's a very foundational principle for dealing with inequalities. All right, now when you deal with polynomial inequalities, generally larger than degree 1. If we have a degree 1 polynomial, it's just a linear inequality. And those we've seen before, those we can solve. A linear inequality like 2x plus 5 is less than negative 9, for instance. You can solve this just by using principles of equality, adding or subtracting the same amount to both sides, like the 5. This would be negative 14, and you divide by the 2. Dividing by a positive doesn't change the sign. If you divide it by a negative, it would change the sign. These are just simple facts for linear inequalities, okay? But anything above linear, quadratic, cubic, quartic, you can't just go through these steps. The inequality properties aren't really useful, okay, when you start working with things that are bigger than first degree. All right, so what we really need to do is identify the zeros of the polynomial and then test to see whether the function is above or below the x-axis at those points. I'll give you an example. If I started out with a polynomial inequality like x squared plus 3x minus 10 is greater than 0. This is a polynomial inequality. Of course, there is a 0 on one side. That's going to be very important. You must have a 0 on one side to make this technique work. All right, so what we're going to do is I know that this polynomial is greater than 0. That means positive, right? It's going to be positive, and the only time it can switch from positive to negative is at an x-intercept, or at a 0 of the function. And so first I'm going to find the zeros of my polynomial. Okay, that's going to be the first step. So let's go ahead and try that. Well, the zeros come from finding the factors of this thing, or setting it equal to 0 and solving for x, right? So x squared plus 3x minus 10 equals 0. If I factor this, x plus 5 and x minus 2 are going to be the factors, because 5 and negative 2 are factors of negative 10 added to 3. And then, of course, you set those factors equal to 0 to find the zeros. And you will find that 2 and negative 5 are the zeros. So those are the only places, those are the x-intercepts, the only places where the graph can switch from positive to negative or negative to positive. But remember, the graph may not switch. There are times where the graph won't switch, particularly where they have an even multiplicity and just touch the axis. So what we need to do is analyze the graph. And really all we need are where the graph is positive versus negative, right? I only want to know where this polynomial is greater than 0 or positive. And so when I look at my intervals, negative 5 on the left, 2 is on the right, there's only 3 possible regions where the graph can be positive, okay? Either on the left, in the middle, or on the right. Because these 2 points, negative 5 and 2, are where the graph touches or crosses the x-axis. So, to figure out which region the polynomial is in, either above or below the axis, it's very simple to just take a number in each of these intervals, plug it into the original function, and see what you get. If you get a positive, then you know that whole region results in positive values. If you get a negative, the whole interval there will result in negative outputs. Okay? So let's try that. Let's take a number, a simple one, right? In this middle interval is 0, right? I love plugging 0 in. It's probably the simplest one. If you can do that, it will help make things quicker. If I plug in a 0, 0 plus 0 minus 10, right? Well, 0 plus 0 minus 10 is negative, right? All I need to know is that that's a negative value. I don't need to know the actual value, just whether it's positive or negative. The negative outweighs everything else, so it's negative, which means this interval is not part of the solution, because I want the polynomial to be greater than 0. So I want to get positive values for that polynomial. So let's try the other 2 sections. Let's go to the left here. I just need any number that's less than negative 5. Maybe negative 6 would be a good one. All right. Now some people will take that negative 6 and plug it right into the original function. That's what I did with the 0. But often it's easier to plug it into the factored form, and you'll see the factors work out a little bit nicer. So if I put negative 6 in here, you would get negative 6 plus 5 is negative 1. Negative 6 minus 2 is negative 8. Double negative makes a positive value. Okay? Again, all I need to know is the sign of that. Again, a negative times a negative is positive. And if I were to plug negative 6 in up here, I would guarantee to get a positive value. Okay, it would be 36 minus 18 minus 10. The positive 36 is bigger than the 2 negatives, so it is positive value. So this is a good region. This is what we're looking for. So the first answer, the first part of the answer, is going to be that interval from negative infinity to negative 5. Okay, that's definitely part of the solution. I'm going to put a parenthesis on the negative 5 because I'm not actually including in my original inequality an equal sign. I don't actually want the polynomial to equal 0, which is what happens at the 0, at the endpoint. Let's try a number over on the right. Number on the right is I don't know, 3 maybe. Doesn't matter what it is. Like I said, it can be any number out there. I like the number 3, it makes the arithmetic nice. If I plug in a 3, 3 plus 5, and again I'm going to the factored form, but you could go to the original, it doesn't matter. 3 plus 5 is 8. 3 minus 2 is 1. 8 times 1, that's a positive number. Again, I don't care what the actual value is, just the sign of the value. Okay, so it gives me a positive, so I know that that region is part of my solution. And so the other part of my solution here will be from 2 to infinity, again, excluding the 2 because I don't want to know where the polynomial equals 0, just where it's greater. Okay, so that gives me a pretty good idea. This little diagram here is what we call a sign chart. I will be asking you to solve inequalities using a sign chart, so you have to write all this out. It's called a sign chart because it determines whether the function is positive or negative in each of the corresponding intervals. Okay. In fact, oftentimes you'll see this written in I will start to do this. I'll sort of separate off the interval and then write pluses over here because all of the inputs result in positive outputs. In this region I put some minuses because all the inputs result in negative outputs. And here I might throw some pluses because all of the inputs result in positive outputs. But the main idea is that you know which intervals contain the positive and negative outputs to the function. Okay, so how does this relate to the graph? Well, let's just picture this for a moment. This graph is quadratic, right? It has a parabola as its graph, and it opens upward with x-intercepts at -5 and 2. Okay, so I can just give a real quick sketch of that graph. Over here is -5, over here is 2. I've got those as my x-intercepts. The graph opens up, and so in between those points, not very symmetrical here. See if I can get that to look nicer. Okay, my graph looks something like this. Now, on this interval, if I were to plug in values for x that are over here in the left interval, the outputs are positive, right? They're above the x-axis. In the middle here, my x values result in negative outputs because they're below the x-axis. And on the right here, when I plug in x's, it's going to result in, again, positive outputs to get to that graph, all right? So wherever the graph is above the x-axis will result in positive values. Wherever the graph is below the x-axis would result in negative. And if it's right on the x-axis, that's where it's equal, okay? We'll do a few more examples, and then we can relate them. When we get larger polynomials, we can relate them to the graph, and you can see how this sign chart really simplifies things, so we don't need to know all the details of the graph, especially for larger polynomials. All we really need to know is one function value in each interval, because I know as soon as one value, like here in the middle, one value gives me a negative output, that means all of them are negative in that interval, okay?